video is still continuing with chapter 3, but now on relative motion and velocity, which is going to deal with sample problem F. So looking here at relative motion, we're looking at velocity measurements differ in different frames of reference. So for example, two observers at different positions while observing the same object may not agree upon the movement of that object. Think back to chapter 2, guys. What was like one of the very first things that we told you that you have to have in order to say that object was moving at a constant velocity, that object was speeding up, that object was slowing down, that object's traveling backwards? You have to have the same frame of reference. So if you have different frames of references, then you don't really know how the object is traveling. So you need a frame of reference in order to say that this object is speeding up, slowing down, moving with 2D motion, moving with 1D motion, that kind of a thing. One object cannot be moving while the other one's at rest and expect to get the same results coming from that. Okay, so think about this. So this plane is dropping a package, and as the package falls, it looks like the package is always in the same position relative to the pilot, right? Like, check this out. Like, it's the same distance between them each time. So when you are watching the package fall, see how the displacement is getting greater and greater, showing that this package is falling down. But also, yeah, it's still in that same position relative to the length of the pilot to where the package is dropped. But what are you seeing this package doing? You're seeing this package follow a parabolic path, a trajectory, right? So this object is utilizing the x and the y axes simultaneously. This one is displaying 2D motion, whereas this one's only displaying 1D motion. It's always in the same position as you're going. Okay, so moving right along with that idea, here's another visual. And get up and try this. Like, seriously, get up and try this. Make sure you have something in your hand, okay? Preferably a pen or a pencil. So while walking in a straight line, disregarding air resistance, you drop your pencil. Discuss the path of your pencil, of what it would take while you were still walking. Where would the pencil land in relationship to your body? What path would the pencil seem to take while it is falling to the ground while you're still walking? And who would witness this pencil making a parabolic path of motion? Okay, so get up. Seriously, get up right now. So you're up, you got the pen in your hand. Either walk towards your computer, walk away from your computer, walk. Like, take 4 steps. When you get to the 4th step, drop the pen and then take 2 more steps forward. Look down. When you drop on step 4, look down where it lands on the floor on like step 6 or whatnot. So it looks like the pen just falls down with you. Like, it's falling with you as you are walking. It's not going straight down. Guys, stop and think about that. If it was going straight down, wouldn't it land behind you? So it's moving forward because of the tendency to resist change. And the tendency to resist change is called inertia. And really, realistically, we're not getting into inertia until chapter 4. But got to explain to you, well, why is it moving forward? It's not like you're shoving it forward. The object was moving forward with you while you were holding on to it. So when you let go, oh, bummer, I still want to move forward, but the force of gravity is pushing it down at the same time. Therefore, it seems to take a 2D motion path. Now, you as the dropper do not see it moving in 2D, right? Because you're thinking that it's falling straight down as you are walking with your pencil that's falling, right? But now go do this in front of mom, dad, brother, sister, whomever, someone else at home. And they'll see that it looks like it's falling forward and down at the same time. So once again, different frames of reference. You're moving, they're stationary. You moving, it looks like 1D motion. Them stationary, it looks like 2D motion. Once again, falling forward and down simultaneously. Okay, so relative velocity, you need to go to this link here. I can't do this right now with this slideshow, but what it's going to show you is that as you are traveling this way across the river, the current is flowing this way. So ultimately, your boat's going to end up right here. It's not going to end up where you thought it was going to end up. So this triangle is really what you come up with. So figure out your actual magnitude, figure out your actual direction of travel. But it's a pretty cool little setup there. So do go to physicsclassroom.com and check out your vectors notes. Okay, some terminology here that we need to go over. First thing that I would like to go over with you is a headwind. A headwind is you are flying and the wind is coming at you. So it's taking you so much longer to get to your final destination. Where you wake up in the morning, you check the flight plan, and it's like, oh yeah, we got some winds that are coming out of the east heading towards the west, and you are heading towards the west. You're flying out towards the west coast. So yay, tailwind. It's not going to take us 3.5 hours to get there. It's only going to take us 3 hours to get to our final destination. So a tailwind would be wind coming from behind the plane, which is thus helping it move faster. And then finally, a crosswind is blowing you off track. You're heading north and south, and the wind is blowing east and west. So you got to try to fight it to move through. So do understand the terminology used here of headwind, tailwind, and crosswind. So plane in the air, and this comes, this comes directly from physicsclassroom.com. Please check out the sample problems on physicsclassroom.com. You will be grateful. Okay, so it says a plane can travel with a speed of 80 miles per hour with respect to the air. Determine the resultant velocity of the plane, magnitude only, don't worry about direction, if it encounters a 10 mile per hour headwind. Well, if you are traveling 80 and you have a 10 mile per hour headwind, does that mean that it's going to be working with you or against you? Headwinds work against you. So that should be a positive 80 and a negative 10. So therefore, you're really only traveling 70 kilometers per hour for this first half right here. Okay, now let's check out B. B says a 10 mile per hour tailwind. Oh yay. That means that you're really traveling 90 kilometers per hour. So you can see how right there you're saving time. Oopsie. So instead of traveling at 80 kilometers per hour, you're going to be moving much faster, therefore getting to your final destination in a shorter amount of time. Okay, let's look at sample problem F here on relative velocity. It says a boat heading north crosses a wide river with a velocity of 10.00 kilometers per hour relative to the water. Please write your givens down the way you see them, guys. It's the most sad thing as you're a teacher. You know, like one of the saddest things is that your work will be absolutely stellar, but your final answer has the wrong sig figs, and I go back and look at your givens, and it's like, well, they decided to just write 10 down. So they kind of sort of deserve to miss that point, right? It's 10.00. That's 4 sig figs right there, not just the number 10, which only has 1 sig fig. So please write what you see. Anyways, the river has a uniform velocity of 5.00 kilometers per hour due east. Determine the boat's velocity with respect to the observer on shore. So you still need to draw this diagram, but just kind of moving over it. The boat was heading this way, the water is heading that way. Here's my resultant, here's my theta, okay? So the first thing that I know jumping into this problem is that I have a velocity in the y direction, and my velocity in the y direction is a 10.00 kilometers per hour. What's theta for this y right here, guys? Just out of sheer curiosity. That should be 90 degrees. Okay, you're moving at 90 degrees right there. Okay, so your v sub x is now the water, and the water is 5.00 kilometers per hour due east. Is 5.00 kilometers per hour due east a positive vector quantity or a negative vector quantity? Yeah, east is going to be a positive vector quantity. And if you're heading due east, your theta in that scenario should be 0 degrees. Okay, so then ultimately it's asking you, so where's this boat really going to end up? So v sub r equals, I don't know, kilometers per hour. Really, truly, the thetas are just in there for you guys to practice. Right now, you aren't necessarily going to use them in the problem. Okay, the other thing that we need to solve for is our resultant. So where is the boat going to end up? And it may be a blank of a blank, just because it says north and east, okay? So 10.00 kilometers per hour due north, 5.00 kilometers per hour due east. Okay, so to solve for the magnitude, we want to use your v sub y squared plus v sub x squared equals v sub r squared. So the square root of v sub y squared plus v sub x squared equals v sub r. Please put this in your calculators. 10 squared plus 5 squared equals square root second answer equals. You should get 11.18. Looking at your givens, you want 3 sig figs from your 5.00. So your 3 sig figs, the 8 rounds that one up. So you really have 11.2 kilometers per hour for your v sub r. Okay, now theta. Theta is the inverse tan of opposite over adjacent. Guys, what type of triangle did you draw here? This is an example of an hourglass triangle. Okay? So that would mean that you want your x, v sub x, over your v sub y. So that would be the inverse tan of 5.00 divided by 10.00. That gives you a total of 26.56. therefore giving you a final answer of 26.6 degrees. And then how's this guy look? Did you go east of north or north of east? Did you go east of north or north of east? You went east of north. Box it. Move on to the next one. Okay, so the next thing we're going to talk about is this real life example. What a great video. Definitely watch this video. It's kind of interesting, to be honest with you. But we will be looking at it in class as well. But clearly it's not from the States. It's not from America. But it definitely has real life applicability into it. And then we're going to move on to projectile motion, which is D and E. So we'll catch that on the next video. All right, so look at your sample problem F here. Work out your practice problems F. Check online to the link that has the Chapter 3 practice problem answers. And looking at your F, you should have a total of 6 answers for your practice problems. So great job, guys.